All right, so 54, page 740. I can remember this from Carpenter versus Construct, an elliptical table from the top from a sheet of plywood. So the plywood is 4 foot by 8 foot. Oh, okay, cool. I like it. So he wants to make the largest possible ellipse. And so what's the most obvious? If I want to cut the largest ellipse I can, I'm obviously not going to cut that ellipse out, right? I mean, why is it obvious? And I could draw, and I'm not going to cut that ellipse out either, am I? I'm not going to cut that ellipse out either. Why are all those obviously not the best ellipses I can?
They don't touch it.
They don't
touch.
They don't touch. Yeah. So this is this 4 and 8 feet are automatically part of the ellipse itself. They talk about some lengths of something interesting about the ellipse, right? So if I have to touch at each corner, at each middle part there, right? Draw Stewie's head in there. Bit back button. My head does not look like it. So how does this, for example, so the center is going to be here. My foci are going to be somewhere here, right? Anyway, my foci. But what's this length here, for example? What's that? That's 4. Right? And that somehow relates to something. So you can actually get the equation for this thing, straight up, right? You can get the equation for the largest ellipse. So what are they asking for? They just want to know what the length of the string is. Okay, all right. That's all I'm going to say for right now, just to get you started. Is that enough to get you started?
I kind of got far enough to get the equation, but I don't really know what to do up until...
Oh, sweet. If you get the equation, remember what's got to be true about... What's the whole point of these things? Whatever point I go to, what must be true? Not that the distances are equal, but that the sum will always be the same, no matter where I am. So whatever this distance is and whatever that distance is, it's the same as if I was here. The sum of those distances is the same. Now the distances don't stay the same, obviously, right? But the sum of the two distances has to be the same. So there is a place where you could put that point that would make that so easy. And that's all I'll say, right? That's a stupid place to put the point. That's a stupid place to put the point. There's a lot of points you could use. There's a very smart place to put the point so that there's not a lot of work involved. I don't know. Maybe, Joe. All right, so I'll let you keep going. So there it is. So you kind of give it away. Just put them there and see what happens. You're trying to figure out how long these strings should be. Well, if you find a good, smart place to put the point, you figure out how long the strings are there. That's how long this... Well, it's only one string, right? But how long must that string be? Well, its length will stay constant all the way around. Because if you add up this piece of the string to that piece of string, it's always the same. So you just need one piece of string. I like it. So if you think about it, can you imagine if I put bolts there and there, and I put like a loose piece of string, and I took it taut, right? So let me pick this up like that. So I put bolts like that, put some loose string in the middle, and I take it taut, and then I kind of put a marker in there, and I kind of go around like that, and with a string is pulling me back. I'm going to make an ellipse. That's the whole idea of an ellipse. So this is actually a valid method to make an elliptical table, is to use 2 nails and a piece of string. It's crazy. All right, I'll let you loose on that. Basically, the answer's been given away just about. You just got to put it together and realize it. That's all. Yeah?
48 feet.
Which one?
11.2 feet.
48?
Yeah.
Ooh, yeah, cool. This sounds kind of nifty. So for any ellipse, there's this thing called the ancillary circle. And of course, that's a really good circle for me. It's only got a slight tumor in the jaw there. Let's see, blah, 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 blah. And they actually tell you, okay, I thought the whole point of this question. So they tell you the circle of the radius equal to half the length of the minor axis. So the radius is 1/2 the length of the minor axis. Which kind of makes sense because the minor axis would be here, right? So the radius would be half that. Let me stop there for a second. You guys kind of with me? So you throw a circle into the center of an ellipse, so they both share the same center. You let the diameter be the minor axis, so the radius is the semi-minor axis length, right? Okay, cool. So that's an interesting connection. What do they ask you here? Blah, blah, blah. Find an equation for the circle, ancillary circle of the ellipse x squared plus 4y squared. Oh, come on now. So since they tell you, I'm sorry, I didn't mean to say that. They tell you the most important part. You got it?
Yeah, it was B.
Oh, it's part B.
Yeah.
So part A is simple. Part A is simple. The minute they tell you this fact, part A is simple. And I like that David's like, yes, Duke, I agree with you. Part B, let's see what's part B say. Oh, cool. I like it. Ooh, that's nice. I like it. Sorry. So if, where'd it go? Come back to me. If ST is a point on the circle, show that 2ST, so this is a, let me put it over there so we can have it be positive one. So let's say this is a point ST. So it's ST. So then 2ST has to be on the ellipse. It's nowhere near as difficult as it sounds. For part A, you've got the equation of the circle, right? So then you say, given that ST works in the equation for the circle, given that that works here, show that that works there. Try it. You can do a few specific examples, but you have to prove it in general. Right? And one thing you can do is, if you plug ST in, you can solve for T. You plug it in this and see that 2S comes spitting out. Right? That's I basically just gave it away if you paid attention. I do that. But now you got to actually do it. Right? Alright. I like it. Coolness. Alright. Those are some of the questions I expected. Cool. Anything else from homework before we get into hyperbolas again? No? Are you guys doing all right? I worry about you. Yes?
11.1 number 50.
50? 50? 50. Okay. So what's it say? Find an equation of the parabola. So they give you, oh, this poor little dude. Who else is here? Oh, it's just gone. Okay. Let's see. So 50. Oh. So they give you this. They give you this picture here. Here's the focus. I tell you there's a line. There's a line that goes through the focus. Let me make this more to a point here. Goes through the focus and then hits here at 2. And the slope is 1/2. Okay. All right. Oof. And then I say, find the equation of the parabola. like this problem. Huh?
This is when we have to use the quadratic formula.
I don't know. So what's the general equation of the parabola, especially considering where its vertex is? What's the general equation for that parabola?
X squared plus y squared.
Parabola.
X squared equals 4py.
Beautiful, because I know it opens up and down, so it's going to be x squared equals, not y squared equals, blah, 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 blah. All right. So if I can figure out what p is, then I'm golden. So the whole point of this problem is to try to figure out what p is. So, the minute I say this next thing, it's going to be too much. The focus and the line they give you, what's the connection? Well,
The slope passes through it.
The slope passes through it, but be more specific. Why is the focus a very special point for the parabola? For the line, sorry. It's the y-intercept, and that's all I'm going to say. That's too much already. Believe it or not, that is too much. So to get this equation, the only thing you need is what? The value of p. All right. What's the value of y? Everything. So we got that. And what does p have to do with the focus? Especially because this vertex is at 0, 0.
It is the focus.
Basically, yeah, 0p is the focus. So I've said too much here. I've said too much. That's it. That's all I'm going to say. So if some of you guys are like, just a little more, I have no idea. I'm too damn bad. Sit down and figure out what I already told you. I love that problem. That problem looks like, what? It's a line that runs through it. Great. That's a stupid math movie or something, like a river runs through it. But it doesn't help me figure out the problem. Yes, it does. It totally gives you everything you need. All right. Anything else? All right. Let's get into hyperbolas. We did real quick last time. We did some stuff, and let me just do a couple of explanations about the technical aspects of this. Remind me about, like, horizontal asymptotes. What was the main idea behind horizontal asymptotes? So we looked at them in the context of something like this here. No, that's
vertical.
good. I like it. So that is a type of asymptote, but this is
It's basically the coefficient, alright?
why. That's a shortcut based off the idea.
So if you divide it by the highest degree.
No.
Alright.
But why would I do that? Why? What's the main idea behind a horizontal asymptote? So if I have a vertical asymptote, could my function do this?
No.
Hell no. But if I have a horizontal asymptote, could my function do that? Hell yes, as long as what? What's the idea of a horizontal asymptote then? If it can just go through it. It's not really a wall then, is it? What is it? What is it? Guideline for what? What it must do eventually, right? When x gets really... Now we got it. So the whole idea of a horizontal asymptote is what's the behavior when x gets big? Negative or positive? Cool. That's what fuels everything we do, is because it's all about what happens when x gets big. You guys with me? That's what I mean by, you can memorize a bunch of shit, but if you really understand the base idea, you got less shit to memorize, because it connects everything. That's the connection of everything right there. That's why we do anything with horizontal asymptotes. So this one would be 1/2, because if I divide by x, I get 1 minus 1 over x, 2 plus 5 over x. When I let x get really big, the limit as x goes to infinity, I think I've used this notation before with you guys, of this is what? When x gets really big, what does 1 over x do? Goes to 0. Goes to 0. So this is 1/2. So the shortcut is the coefficients, the ratio of the coefficients of the highest degrees, right? They're equal degrees. All right, how we doing? Remember those days? Right? And you're all like, Okay, Jeff, just wanted to go back. So the connection this has with what we're doing now solve this for y. Because if I want to graph this in my calculator, I have to solve for y, right? So what do you get when you solve this for y? I'll do this piece first. Yeah.
And then multiply everything by b. This.
Okay, I like it. So you get b squared x squared over a squared minus b squared equals y squared. Square root, I like it. Square root, square root. So you get y equals plus or minus square root b squared x squared over a squared minus b squared. Over 1, I just put over 1 just so it's all the same level. So the next step is something you guys have to get a lot more familiar with, especially those of you going into calculus. You need to be able to do this next thing relatively easily. Can I take anything out of that square root? Can I do the square root of something in there? Yeah, in fact, I could force the a squared out too, right? So if I factor, let me do this in steps. If I factor the inside like this, can somebody help me figure out what's left inside? I'll do the first part for you. X squared. I'm helpful. Yeah, Jeff, you're funny too. Nope. You didn't just take a b squared out of this. You took a b squared over a squared out.
Negative. So it's negative a squared over 1.
Yes, good. So what's left inside is this. Because what happens when you multiply this back in? A squares cancel, I get a b squared there, which is exactly what I want there, yes. So when you factor something out, you're dividing by it. So you're multiplying this by the reciprocal of what you're taking out. So what's left is the a squared. All right, let me let you guys soak that in. Soak it. Why am I doing all this? Because I want to relate it to this. I want to figure out what happens when x gets really big. That would explain why I had those dotted asymptote things coming shooting out of the corners of my box that I drew up there, right? So now what can I do? Why did I do that shit? What can I do now?
You take the
Square root, so out comes a b over a. Now, let me ask you this. What can I do with that that would be similar to what we had to do here? Let me see if you guys can get this. What would I have to do to this that would be similar to what I had to do there to figure out what happens when x gets really big? And this is let me even do this better. What was the thing we did here that helped me see this next step? We got an x to show up on the bottom, right? So I can't do exactly the same thing we did here because I don't really have a ratio of things on the inside there, right? But I could take x squared out, so it would come out as what? Stay with me now. What would it come out as? Square root of x squared is? X. Let me see if we can just bypass this shit we just did. So I effectively divided inside by x squared, right? I took an x squared out. So what's left inside?
The second over x squared.
Yeah. 1 minus a squared of x squared. Now what happens when x gets really big? Think about the inside first, because that's going to grow faster than that will, right?
Yeah, it approaches 0.
So this approaches 0, so the whole thing approaches
1.
b over ax. So this goes to 0, so the square root of 1 is 1, so that approaches this. That's why those are the asymptotes.
It's not exactly that, is it?
It is exactly that. Why do you say that though?
Does x ever actually get to 0?
I love it, I love it. But what's the whole idea of an asymptote?
Got it.
You never get there. It's a guide. It tells you, oh yeah, you will approach me. You'll never get to me. Talk to Zeno. Alright, remember Zeno? The guy trying to get to the town. Did I talk about Zeno in here? Zeno's paradox? Alright, so stop looking at me blankly. What's up? Oh yeah, the infinity thing. You can divide something up in infinitely much. Right? But somehow we always make it to where we're going. It's good. Okay. Yes, sir.
How did you get rid of the a squared over x squared? Like, how does that?
When x gets really, really big, this goes to 0.
Okay.
So this goes to 1. Cool. And I'm not going to put infinity in here because I just want to know what does it look like. What's the guideline as x gets really, really big? It's that. So let's put this all together. Let's do an example. Let's remember how to do this. And the funny thing is, well, I'll show you what the funny thing is. So let's see, I think last time we did one that was on the x-axis, so let's do one that's on the y-axis. Oh, what you got, Jeff? I don't know, Jeff. Yeah, sure. Well, let's make it a minus so it's actually hyperbola. So just to make sure everybody remembers the first step, what's the first step? Good. So the first step for an ellipse and a hyperbola is to get a 1 on that side. So divide by 81. So we get y squared over 81 minus x squared over. So what's, and again, let me see, what's the book's convention for this? Yeah, okay. So what the book does is, it's funny, for ellipses they forced a and b to be defined so that the focus equation was always the same, because it was a squared minus b squared. Does everybody kind of remember that? And I try to talk a little bit about who cares what a and b is. But if you try to set up a general formula for it, you have to pick something. And it always makes it sound like it's harder than it is. So here, instead of making this equation the same, they switch what a and b is, so that sometimes it's b over a and sometimes it's a over b. Here's the beautiful thing. What is b over a in that equation? What does it act as? The what? Beautiful, which is the slope. And what's always on top in the slope?
The y.
The y, right? So look what letter's on the top here.
Y.
That's b. And where was b? It was with the holy shit and a half. So who cares what you call a and b? If I want to find the equation of the asymptote, I put the number that's associated with the y on top, and the number associated with the x on the bottom. That's going to be the slope. You guys with me? A little bit. That's that simple, right? The formulas make it look like, what's A, what's B? That's so critical. No, it ain't. It's not worth shit. It doesn't matter. All right. And another reason why this is definitely not as critical anymore is the focus formula. This has got a minus in it, so the focus formula has a. So now, unfortunately for you, it looks a lot like Pythagorean theorem, which doesn't necessarily mean that. It's just a distance formula, so that's what Pythagorean theorem comes from. All right. So what can you tell me about this hyperbola? What's it fundamentally going to be shaped like? And what do I mean by that? You're like, dude, it's always a curvy thing. But is it going to be like this, or is it going to be like this?
Up and down.
Good. It's going to be on the y-axis, so up and down. Kick ass. I want to both of those pieces. Kick ass. So it's going to have to be on the y-axis, or at least in the y direction if it was shifted over. Beautiful. I love it, because that's the positive piece. So how far on the y-axis am I going to go? I'm not even going to call anything A and B. Screw it. And this guy, square 9 is 3. So in the y direction, I'm going to go 9. In the x direction, I'm going to go 3. And then I can make my little box, dude. Now real quick, what's the equations of the asymptotes? What did we just say a second ago? To make the slope, you put the y piece over the x piece. That's crazy. So what goes on top? Careful, not 9. No, not either 9 or 81. Well, not 9 for the wrong reason. I'm sorry. My bad. So yes, 9. I'm sorry. Because 9 is with a y. So whoever said 9, I'm sorry. I take it back. And what's with the x? 3. Okay. So it's y plus or minus. I just picked really poor numbers to make that clear for me. I stop there again. Let me see if you guys are cool with that. And with the squares of the a's and the b's, you really only use those for the focus equation, right? I mean, everything else, the lengths and stuff, they're all the a and the b, not the squares. What's the focus position going to be?
3 times the square root of 10.
Square root of 90, right? I like it. So 3 square root of 10. Take that square root of 9 out. Take x. Alright, so there's the focus. There's the equations of the asymptotes, which we found by using the formula that came from applying a limit to the hyperbola equation. Oh my God. I'm going to show you how it just comes out of your freaking box. Right? Here we go. So I want to go 9 in the y direction. Let's see. You can do it, Jeff. 3, 6, 9. Good job. 3, 6, 9. And I'm going to open on the y-axis, right? I'm going to be on the y-axis. So the points I put are actually going to be points. That's truly a point. That's truly a point. In the x direction, I want to go 3. 1, 2, 3. So I'm going to put a little open circle or something there if I want to. You guys with me as to why that's sort of semi-important? Please don't put straight points that aren't really points on your graph. Use X marks or open circles or something, right? So then I can do what? If this was an ellipse, I'd be done, right? But now, yeah, I draw a box. It probably looks horrible from that perspective. When you're standing right on it, it looks fine. And my scale sucks so desperately bad, but oh well, we'll get over that. If you haven't gotten over that by now, then I don't know what to do for you. Now watch this. This is kind of silly. My asymptotes, I can always just draw them without even knowing the equations. I can just draw them. It's easier if your scale is better. I can just draw them in through the corners of the box. But what must the equation be? How much did I go up? 9. How much did I go up? 9. 9. I went up 9. I rose 9, and I went over 3. Or I fell 9 and went over 3. That's why it's plus and minus, right? Ooh, so do I really need that stupid little equation? No, I don't really need it. I can just draw the freaking things to the corners and look at it. Let me stop there for a second. Yes, sir?
But if it's shifted, then you would kind of need...
Beautiful. Now, if it's shifted, I can still find the slope, and then I just use the center. Does that make sense? So if the center was 2, negative 1, then I would just say y plus 1 equals plus or minus 3 times x minus 2. Let me let you absorb that for a second. This is if the center is 0, 0. This is if the center is 2, negative 1. You guys alright? See, even that's not a big deal. I would still just count up and over, even if it's been shifted, and then just throw the center in there. And what's this the center of? What would this be the center of? The hyperbola, or the imaginary ellipse in the center. I like it. Alright. Cool, I like it. And now, how do I draw my hyperbola? Very careful. Just follow my guide. Coolness. It looks just so awesome. Especially if you stand right here. It looks pretty good. If you stand over there, I'm like, oh my God. Alright, so let me shut up. Here. You guys work on this. says two shifted and two non-shifted conic sections. You can work together or alone.